Hello everyone. Welcome to today's live interactive session on geology and soil mechanics. So, today's session is technically the last session for all the 12 week of this course. And today, since it is the 12th week, it will be technically the last, but tomorrow, again, from 6 to 8, we will be having one more last revision session. Okay, so we won't be solving any problems or okay, doing any more technical stuff tomorrow. Just we will be revising from the first week to the last week, that is today's week, whatever today's class, whatever we have studied, all those things we will be studying. We will be spending 10 minutes on each week's slides. We will just go through, we will skim through all the topics very fast. So we'll skim through some problems very fast, and then we will just wrap up this course. So yeah, so that's all. Let us begin today's session and hope that all these sessions were quite helpful to you, and you have actually benefited from these sessions. And I hope that all of you are preparing well for your exams. So, of course, those of you who will be giving the exams, obviously. So, I hope that you are preparing well for the exams, and all the best for your exams. Yeah, so just practice all the problems properly, all the concepts, try to go through all the concepts properly, and there is no doubt that you will perform well in your exams, right? So let us begin today's session by solving directly solving some problems, right? So let us just start slowly. uh, just a second, let me just uh, find it out. Okay, so let's see this problem. So retaining wall with stratified backfill and surcharge is drawn. Estimate the resultant thrust and its position. Okay, so I'll just draw the retaining wall first. Okay, so this is the arrangement of the soil layers. Now, uh, right, so this is the expression for the active earth pressure. It will come out as active earth pressure coefficient will come out as 1 by 3. So first at the top, you will be having, due to the surcharge, you will be having one this arrangement, right? So this is nothing but 10 times K1, and you'll having one more angular arrangement, and this is nothing but 15 times 3 times Ka. Right. So my small Pa1 is 10 into 1 by 3. Okay. Pa2 will be 15 times 3 times 1 by 3. Pa, I put capital Pa1 equal 3.33 into 3. All right. Okay. Now let us see for the bottom soil layer. So our bottom soil layer again we will have one surcharge like arrangement. This will be Pa3, small Pa3, and again angular arrangement. What? Pa4. My A2 is at 0.704. Now A3, but first is the surcharge, or surcharge that is there from that, and the now the surcharge from the upper layer of soil, that is 15 times 3, okay, times Ka2, which is 0.704. This one will do it. Only ah. Now see the bottom soil is C5 soil, right? So if it is C5 soil, you will be having uh, a kind of this zone that comes. It's like the negative zone that comes, right? So that we just write the negative part separately, okay, and denote it as PF4. Just remove this from here. Okay, it's 2IC root over K2. 0.04. Just a different way to solve. Okay. All right. And lastly, we'll have the PA5 is nothing but K2 Z. Z is what? Z is what? That height. Mm, right. So now my total PA is nothing but so generally due to that negative thing we get a pressure something like this, right? So now I have considered that uh, I am having I have considered this as equivalent to the negative minus and then this some positive, okay, some positive. So this will combine give me this. So like this I have considered it, okay. So this and you have okay, this part is the minus part and you have this positive part. So if you my and this part will go, so I will get this and this. Understood, right? I hope you understand this. Okay, so this generally are what? Are it's something like this, right? Something this is negative. This is what nothing but this part is was minus twice c root over k. Okay, and this is uh gamma z k minus twice c root over k. So this is nothing but what? If you, so this and this, right? So this part is getting cancelled out. So hence you are getting this. I'm just separately I'm doing this and this. Okay, that's all. That's my this is my P4 and this is my P5. Okay. Okay, so we got the P, the Y, 9.99 times 3 plus 3 by 2. That is 1.5 plus 22.5 times 3 plus 3 by 3. It is 4. 4 and plus times 3 by 2 is 1.5. Then you have minus 50.34 times again 1.5. Then you have last you have plus 63.36 times 3 by 3, that is 1 times by 161.68. Get from the bottom. Okay, it's a wall. So but here P is Y. All right. So solve this and check the results by yourselves. Okay, there might be some mistakes or I might have done something. So you please solve and yeah, so check the answers. So let us see the next problem. The section of a cantilever retaining wall is drawn below. Find the factor of safety in sliding, overturning, and bearing. Okay, so let us see how we can do this. So you have a retaining wall with a backfill. You have a surcharge. Okay. So this thickness is 0.5 meters. This thickness is 0.4 meters. This is 2 meters. And from the top to bottom, this is 6 meters. Meters. So C prime is given as 0. Phi prime is given as 41 degrees. Magnitude is given as 16. Alright, and you have the bearing capacity, safe bearing capacity of the foundation soil as 200 kiloton. Okay, so this is the arrangement of the cantilever retaining wall that is given to us, and we are asked to find the factor of safety in sliding, overturning, and bearing. It means uh, how much factor of safety the retaining wall has against the lateral earth pressure that is acting. Okay, that is the one that is that might cause the sliding, right? So that, and then we have the overturning. Same, the earth pressure is the disturbing force that is trying to overturn it. Okay, and finally the bearing also. You have to check. Okay, let's do this. Okay, so we got the Ka, this, and then we have the A. PA is what? K times gamma Z plus Q, right? That's all. Total pressure. This is the pressure. So from here we can get 0.2077 gamma into Z plus the pressure 35. Okay. So this one will come out as all right. Right. So total PA. So total PA will be 0.2077 into so this means half 6, right? This is how much would be C1's 0.5 times 0.2077 and 5 times 0.2077 times 15 times 6 59.2 plus 0.2077 times 3.61. So 103.41. Okay, so let us call this as capital P1 and this as capital P. Okay, for later references. Okay, so that it's easier for us later on. Right? Okay, so here this is my P1 reacting rectangular arrangement, and P2 is what? P2 is my time arrangement. Okay. So now what we'll do, we will just write all the forces, the moment terms, and then we will calculate the moment, the total vertical load, all the stuff we will be calculating next. Right? Okay. So first is my this P1 and P2 forces. Forces. What is the momentum? Momentum is nothing but the distance from the bottom. That is 6 by 2, we get 3 meters. And so moment if you multiply this to this, you will get, yeah, next to 59.82. That means 6 by 3, that is 2 meters. Next to weight of stem. But it's nothing but 24 kilonewton. We can take the fuel concrete times 5.5 times 0.4 is 52.8. Okay, we have 2.2, right? 2.2, 6 by 2, no, 5 point to say from the bottom you are taking, right? So the stem is 5.5 meters high. All right. So yeah, right. So see, so that will be acting somewhat. So if this is the stem, it will be acting somewhat at the center of the stem, and we are taking the moment. What we are doing, we are calculating the moment about this. Okay, heel. This red dot, that is the heel. So from here, what is the distance of this center? So we have this, right? So it is from here to here. It's how much? 2 meters. This is 2 meters. This is 2 meters, and then 0.4 by 2. That is 2.2 meters. Okay, this is zero point 0.4. So this by 2 is 0.4, zero point 0.2, and from here to here it's 2 meters. So 2.2 meters. Yeah. And then we have the weight of the base. It was 3.5 into 0.5 into 24 will give us 42. And the distance is 3.5 by 2, that is 1.75. That's 73.50. Then we have the weight of backfill. Weight of backfill is what? 2, 2, this 2, 2 times this height, 5.5 times 16, 2 times 2 times 5.5 times 16, it is 176, 76, and this is going to be 1 meters. Okay, and then at the last you have the surcharge. Surcharge is how much? 3.35. So 35 times our 35 times 2, it is 70. And the distance is again 1 meters. $70. So now if I total this, I will give the total moment that will come out as 685.71 meter. Okay, check this value, huh? Check the addition, check this value yourself once. Then we have RV. RV is is 2.01 meters. Okay, so this is the X bar is nothing but the center of my the forces, center of application of all forces, you can see. All right, and the yeah, okay. Okay, so therefore you can have eccentricity E is X bar minus P by 2. Okay, so X bar is the centroid of the all the loads, centroid of the loads. That minus V by 2 will give my eccentricity about the base to 6 meter. Okay, 0.26 meter. Now this should be eccentricity should be less than B by 6 always. You know that, right? Less than B by 6, so that there are no tensile pressures that develop at the base of the retaining wall. Okay, so what is my B? My B is nothing but 3.5 meters. So it's 0.58. B by 6 is 0.58. So 0.26 is less than 0.58. So there are no issues. Next, we can calculate the base pressures. R by P. Okay, so this is less than the safe bearing capacity, so it's fine. And then again, we can have the Q min. So this is positive, so it's okay. Now factor of safety sliding RV 10 delta by RH. So RV, this is nothing but the an angle between the base soil and base of the retaining wall. Okay, so generally it's taken as 2/3 of pi. Okay, so we can write this as 340.8 times 10. That is okay. Now one more thing we have to calculate. So we already calculated the factor of safety in sliding. So what we are left is the factor of safety in overturning and bearing. So how can we calculate the factor of safety in overturning? The factor of safety in overturning can be so we already have the what do you say the mm, uh, we will calculate the overturning moment. Right, we can calculate the overturning moment. Overturning moment is nothing but a P or P times the lever arm. Okay, that will give me my overturning moment, and my resisting moment will be nothing but all the downward forces. Okay, all the downward forces that are acting. Show you. So this is the sliding. You got the sliding vector of safety. Okay. And just 1 second. So then you can calculate vector of safety overturning. So this is nothing but uh my resisting moments, sum of resisting moment by overturning moment. So what are the resisting moments? Resisting moments are, so you have the retaining wall, right? Like this, like this, like this. So all the downward forces that are acting, that times the lever arm will give you the resisting moment. And my overturning moment is my this PA P times this distance. So just if you just add all these, this will be your overturning moment, and this will be your resisting moment. And if you add these two, this will give you or overturning moment. Okay, so if I add the bottoms, get 116.16 plus 73.5, 176 plus 70, it is 435.66. My overturning moment is to 50.04. Check this, okay? 30.4. Come out as 439.66. To 1.74. Okay, so it's fine. Okay. And last is the bearing capacity. Okay. Vector safety in bearing. So just sum of all the vertical forces you have 340.89 that divided by your bottom what to say this bottom width. Okay, that will give you the pressure. So 340, so that is that will be we'll see that it is less than your bearing capacity. Okay, bearing pressure, say bearing capacity. Okay, so try to do this by yourselves and just think what you're doing and just check if you're able to do. Okay. Just give me a second. I will be back. Just give me a moment. Huh? Just give me a moment.
Just a second. I'll just turn off this and just turn back on. Huh? Just give me a second. I'm just checking one thing. Just check this on YouTube. The second, actually, I'm not able to find something. Okay, leave it. I will see it later. Okay, let us proceed. Rectangular loaded area, 6 meter into 7.5 carries a load of 200 kPa. Determine the vertical stress at a point P located outside at a depth of 7.5 meter. Okay, so let me just write it. Okay, so this is 7.5 meter. This is 6 meter. Okay, and P is located somewhere here. This is 3 meter. This is 1.5 meter. Okay, so try to calculate this, try to find this out. This will be similar to what problem that we solved in the previous class, right? So try to do this, try to do this. Some issue here. Just a second. Think some issues here. Just give me 1 minute. Sorry for the interruptions. This having some. I'm not able to. The presentation is presented well there, but I am not able to see it properly here. So I'm just checking that thing. Just give me some time. It should come hopefully. Uh, so let us. Let us now do it everything very fast. Yeah, so as I was saying, I gave you this question, right? So, yeah, so how we can this is that. So you have this thing that is there with you right now. Can extend it that way. Okay, so the P point is here. Huh. So, what we will do, what we are going to do is that just write A, B, C, D, E, F, G, H. All right, let's say this area is A1, this area is A2, A3, this area is A4. Right. So here to here it's 7.5 meters. Here to here it's 3 meters. Then from here to here it's 1.5 meters. And here it's 6 meters. All right. Now the thing is, if you want to find out here, what we can do, we can find the K value. So our pressure is what? K times the sigma vertical pressure, right? K times the vertical pressure. So what we can do is our z sigma z this sigma z we can have it this way. So sigma z can be written as sigma z is a vertical pressure, right? So K A E P H. So bigger triangle A E P H, bigger, the biggest rectangle, minus K B P B F P H. BFP. So this minus KDEPG. DEPG. Okay, so this A4 area got deducted twice. So just once we have to add this. Okay, plus KCFPG. All right, because this is what? This is for, we know that, say if this is a arrangement, this is a stress arrangement, so below one corner, how to find out? We can find out by this. So how we can use that concept to determine this way? This is how we can do it. Okay, so this is how we can do it. So now what is the K? Right, so this is my expression for K. Now one by one you have to calculate. So now first for APH, 10.5 by 6 KAPH times 3.96 plus 1 by 2.96 plus 2 plus 2 plus tan inverse 2 into 1.4 into 2.96 plus 1, 2.96 minus 1.4 square plus 1. Okay, so we'll get this as, remember to put your set your calculators into radians while you calculate this value, huh? So it is 0.2. All right. Now similarly, EFPH means just 0.058. Okay. Next, similarly for others also you have to do. So K will come out as 0.1013. Okay, I'm not showing the calculation. You do it yourself and check the results. All right. KS. Okay. What my sigma Z is 100 equal to. Huh? All right. So this is how we have to do it. Let's go to the next problem. The plastic and liquid limit of a soil are 30% and 42% respectively. The percentage volume change from liquid limit to dry state is 35% of the dry volume. Similarly, the percentage volume change from plastic limit to dry state is 25% of the dry volume. Determine the shrinkage limit and shrinkage ratio. So, you, let us draw this volume with water content. So you have graph look something like this, right? So here we have the shrinkage limit. Somewhere here we will have the plastic limit. Somewhere here we will have the liquid limit, right? So this here we have the volume. Here we have the water content percentage. Now this volume here, this volume is my dry volume. Okay, this is my dry volume. This is the volume at plastic limit, and then we have the volume at liquid limit. Okay. So it is given that the plastic limit is 30% and the liquid limit is 42%. Also, the volume change from liquid limit to dry state means this this volume change. This is VL minus VD. This is given as 35% of the dry volume. Okay, this is given. And also you can similarly have the volume change from plastic. This one from plastic to dry is 22% of the dry volume. These are all given. Okay, these are given to us. Now taking slope. So we have to find WS. Okay, this WS we have to find out. Okay, so yeah, taking slopes you can get VL minus VP by WL minus WP is equal to VL minus VD by WL minus WS. So VL minus VP means this divided by WL minus WP, right? WL minus WP means this equal to VL minus VD, VL minus VD, that is this bigger triangle. Okay, VL minus VD is this divided by WS, WL minus WS means this. So the triangle slopes are equal. So taking the slopes, you can write this, which implies I can get difference 97, 97%. Stay at the shrinkage ratio. Shrinkage ratio is nothing but PL minus VP by VD, 200% divided by WL minus WP. 0.3 by VD minus this is 9.7, huh? Or 97, 9.7%. By 1.22 VD, VD 100, 52 minus 30 plus 1. Okay, so yeah, very simple. The soil has the following properties: liquid limit is given, plastic limit is given, passing through 4.5 cm is given, and passing 75 micron sieve is given. We are asked to classify the soil. So how can we do that? So we have plasticity index as 40 minus 30, 10%. Now plasticity index from A line 0.73, liquid limit minus 20, which is 0.73, 40 minus 20, think that 14.6%, which is greater than 10%, means it plots above the A line. Okay, the A line. So what will it be? So, sorry, it's plots below 14.6 is greater means the A line is higher. It plots below the A line, right? It plots below the A line. 10% is our plasticity index, and A line from A line we are getting 14.6. So our point plots below the A line. That means it's greatly silt. And what kind of silt? You can classify. So 4.75 mm, how much it's passing? So first you have to see that, right? So 65% pass, more than 50% is passing through 75 micron seams. But definitely it's a fine grained soil. Right? So our kind of fine grained soil, we just saw that it's a silty fine grained soil. Now silt, how can we classify? Low plastic, intermediate plastic, high plastic. So it this will fall into intermediate plastics since the liquid limit is between 35 and 50%. We have 40%. So it's nothing but MI. Let's see one more problem from the initial chapters that we studied. During a compaction test, yeah, during a compaction test, the soil attains the maximum dry unit weight of 18.6 kilonewton per meter cube at a water content of 15%. The specific gravity of soil solids is 2.7. Determine the degree of saturation, air content at maximum dry density. What would be the maximum theoretical density corresponding to the zero air voids at the bottom measurement? So let us recall. So gamma D is right. So gamma D is 18.6 by S. So nine five five, we can think that 0.5%. Now next is air content. So yeah, air content is volume of air by volume of voids, which I can write as 1 minus saturation is 0.045, which is 4.5%. Okay. What is saturation? Saturation is volume of water by volume of voids, right? So air content is what 1 minus saturation, volume of air by volume of voids. Gamma D theoretical maximum is G gamma W. Just here S input 1. It will give you the theoretical maximum. My theoretical maximum is 18.85, but my actual is 18.6. Okay. Next, a layer of saturated clay 5 meter thick is overlain by sand 4 meter deep. The water table is 3 meter below the top surface. The saturated unit weight of clay and sand are 18 kilonewton per meter cube and 20 kilonewton per meter cube respectively. Above the water table, the unit weight of sand is 70 kilonewton per meter cube. Calculate the effective pressure on horizontal plane at a depth of 9 meters below the ground level. What will be the increase in effective pressure at 9 meter if the soil gets saturated by capillary up to height 1 meter above the water table? Okay, just try to do this. Just try to do this for some time. We already know how to solve all these problems, right? We have solved previously also. Just try from your side. Check if you're able to do. I will solve it obviously. Just try for a few minutes. Are you able to do it? That's active crisis and all these things you have to find out. That's all, nothing else. Gamma times unit weight times the heights. That's all you have to do. And then deduct the pore water pressures wherever necessary to get the effective values. That's all. The question seems to be because it's written, it's not directly drawn. But if it's drawn, it's very easy, right?
So you have a sand saturated, saturated clay overlain by 4 meters. So you have a 4 meter thick sand that is overlain by a 5 meter thick clay. So to top it's sand mixed clay. Alright, water table is 3 meter deep. That means water table is here. Is here. This is the ground table. The table is here. Saturated into clay is given. Strengths and both are given. Saturated unit weight. Uh, have the water table, the unit weight of sand that is also given. Calculate effective pressures and relative depth of 9 meter below. That is here. Here you have to calculate. First, let us do. So, what is the total stress? First, let us calculate. So, 17 times 3 plus 20 times 1 plus 18 times 5. Okay, this is 161 square. So this is my total stress. Pore water pressure. What is the pore water pressure? Gamma W times 6 is 9.81 times 6. Therefore, effective stress is 101. So this 102, you can also directly get by multiplying the submerged unit weights, right? Submerged unit weight. Let's say the first it will be 17 times 3
plus 20 minus 9.81 times 1 plus 18 minus 9.81 times 5. So directly you can get 102.14. Next, the question is, what will be the increase in effective pressure at 9 meter if soil gets saturated by capillary up to height 1 meter above the water table? Means 1 meter above it is getting saturated by capillary. Okay, then what will be the change? So now let us see second case. Okay. So now first I will have 2 times 17 times 2 now plus 20 times 2 plus 18 times 5. So this is my total unit weight, total total stress, not even total stress. Pour water pressure 6 times 9.81. Same water pressure is going to be the same 6 times 9.81. Effective stress is okay, therefore increase in pressure is alright. Alright, that's all. So if the water table rise this uh, so what happens here is 1 meter above that above the water table, the soil was also saturated. In that way, what happened? The effective stress increased. Okay. Let's see the next problem. A permeameter of 100 mm dia with a sample length of 30 centimeter used for a constant head and falling head test. While conducting a constant head test, the loss of head was 120 centimeter for the soil sample and the rate of flow was 3.2 centimeter cube per second. Find the coefficient of permeability. Okay, the following head test was performed on the same sample, the same wide ratio when the time taken for the head to perform 98 to 80 centimeter. I have the standpipe following head test work in the following head test work 25 mm. So let us do this is nothing but following head and concentrated test from what that we do to find out the permeability of the soil. Okay. Okay, so try to do this. This is also quite simple. Directly you have to use the your values for this values of your directly you have to use the expressions for the concentrated and following a test. That's all. Just do plus 78.53. Okay, net KQ by IA. So Q is what? 3.25. So 4, right? I into A 78.53. Out of 0.0102 per second. So this was the constant head test. Right, so we got the K. Now next we have the falling head test. Just square is 2.303. H2. So okay, already calculated. So 0.09 into 30 by time log 98 by 50. Right? It's given from 98 to 50 how much time it takes. So 98 by 50. From here we can get ds 3.5 seconds. Right? Yeah. Let us see, a 3-meter thick soil strata has a stratum has a coefficient of permeability 3 into 10 to the power minus 7 meter per second. A separate test have porosity 40% and bulk unit with 21. The moisture content 31%. Determine the head at which upward seepage will cause quicksand condition. What is the flow required to maintain critical conditions? Okay. So first we will calculate the void ratio from the porosity. Also porosity is given. So void ratio I can easily calculate. Now what is my dry unit weight? Gamma by total unit weight divided by 1 plus water content. So my bulk unit weight is 21. 1 plus water content is 31%. This will come out as 16.03. Now gamma D is G gamma W by 1 plus E. So we can get it this way. 16.03 is equal to G into 9.81 by 1 plus 0.667. From here I can get GS 2.72. Okay, the specific gravity of soil solutions 2.72. Now I know my critical hydraulic gradient is what? Nothing but G minus 1 plus by 1 plus C. So G minus 1 by 1 plus 0.667. be 1.03. This is my critical hydraulic gradient. But this is my critical hydraulic gradient. Now the question is, remember the head at which half part shape will cause this quicksand condition. Now, uh, at what head will it cause? So if I want to find it out, what head loss by length, so our head loss is 1.03. Hydraulic gradient is 1.03 times 3, so 3.09 meters. So for a head of 3.09 meters, 3.09 meters, we will get this quicksand condition. Okay, with a head of 3.09 meters, it gets quicksand condition. Now, what is the flow required? KIA. So K it's already given, 3 into 10 to the power minus 7 times 1.03. It's 1. So it will come out as 0.1 into 7 meter cube per second per meter square. Okay, so this is the flow that is required to maintain to maintain this critical gradient at this particular head. Yeah. 1 meter thick layer of saturated clay drained both faces settles by 15 centimeter in 2 years. If a thin layer of pervious soil is introduced in the middle of this layer, then what will be the period during which the settlement of 15 centimeter will be computed? So initially we have a 1 meter thick layer. So both sides it's draining. So in that case, we have 15 centimeter in 2 years. Now we're introducing one more pervious layer in the between. So my drainage path has reduced, right? Drainage path is reduced. Okay, my drainage path is reduced. Then what will happen? Obviously, in the same period of 2 years, more amount of settlement will happen. Right? More amount of settlement will happen. How to do that? How to can we solve this? So TV we have CET by H drainage height square. So you can see here my time is directly proportional to the square of the drainage path. So I can write, if I take two ratios like that, HDR by HDR1 by HDR2 squared. Right now, right now, time required T1 is 2 years when my HDR is 0.5. Okay, so 1 meter, uh, 1 meter. So drainage path is my 1/2, that is 0.5, and time I have to when time is I don't know. Okay. Okay, so I initially read the question wrong. I read that in 2 years' time, what will be the amount? No, the question is that 15 centimeter settlement will now take how long? So obviously it will be lesser time. Lesser time. Initially it took 2 years. Now as you have reduced the drainage path, the time required for 2 years will be lesser. Time required for 15 centimeter settlement will be lesser. So right. So this is done. Now I have to find when the HDR is how much. So now you can treat this as this by 0.5 by 2. It's 0.5 by 2. Okay, it's 0.25 meters. Right. Because here to here it will turn like this. So 0.25 meters. So how can we do now? So initially time was 2, T2, 0.5 by 25 square. So 0.25 to 2, the 4, the T2 is 2 by 4. It is 0.5 years. So hence we can say that if drainage path reduces by half, or if drainage path reduces by half, time required reduces by 4 times. Okay, and last problem for today. A cylindrical specimen of dry sand was tested in a triaxial test.
failure occurred under a cell pressure of 1.2 kg per centimeter square and deviated stress of 4 kg per centimeter square. Find angle made by failure plane with measured principal axis, angle made by plane of maximum shear stress with the measured principal plane, shear stress on the failure plane, and normal stress on the failure plane. Okay.
Cell pressure is net principal stress nothing but 1.2 per centimeter square. Static stress is given as 4 kg per centimeter square, and my sigma 1 is nothing but sigma d plus sigma 3, nothing but 5.2 kg per centimeter square. And given c is 0, since c is 0, I can write my basic equation as sigma 3 10 square 45 plus 5 by 2 plus twice c 10 45 plus 5 by 2. That portion is not there since c is 0. So I can write this from here. If I put all my values 5.2, 1.2, 10 square 45 plus 5 by 2. From here I will get phi as 38.6 degrees. Okay, so now angle made by the failure plane with the major principal axis is nothing but alpha 45 degree plus phi 2, which will come out as 64.35 degrees. Now next is angle made by the plane of maximum shear stress. Maximum shear stress with the, that is nothing but 45 degrees, right? 45 degrees. So uh, circle, I think, yeah. So maximum shear stress, so say shear stress is nothing but here. Okay, so this plane is always 45 degree here. Okay, diametrically opposite point this plane. Always this is now max. This is always 45 degree. So angle made by plane of tau max with major principal plane is 45 degree. Now next is shear stress on failure plane. We have to use this sigma 1 minus sigma 3 by 2 sine twice theta twice alpha will come out as 1.56 per square, and then normal stress on failure plane was sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 cos twice alpha. Okay, I will do cos 1 out as 1.95 per centimeter square.
Okay, so that's all. This is how we do it. This. All right, so this was all for today. So if you have any doubt, you can ask me, and we'll be meeting again tomorrow from 6 p.m. to 8 p.m. We will be just discussing, just revising, we'll just reading whatever you have studied from the first to the end. We'll just spend 2 hours discussing. If you have any doubts, you can ask me. We will discuss some questions, like verbally we'll discuss. We won't solve anything. We'll just go through, skim through all the topics, and we'll just discuss and see. Okay, just revise, just recapitulate what we have studied. All those things we are going to do tomorrow, and that will be the end of today's course. To the end of this course. All right. So let us meet tomorrow again from 6 p.m. to 8 p.m. Okay. So thank you so much for attending the session. Hope this was helpful for you. Yeah, thank you, and have a great evening, great night ahead. And if you have any doubt, you can stay, you can ask me, or else you can leave. All right. So thank you so much for attending.